Right, so let's begin. I'll share my screen. Just a second. So let's begin. Hello, everyone. I'm Srishita. I am a PhD student associated with the Center for Systems and Control at IIT Bombay. And I'm also the TA for this course, WE46 Linear Dynamical Systems. So welcome to the third week's tutorial session. So we will begin by recalling the concepts, discussing the lectures. So see. So we'll cover the following topics. So we'll talk about how to compute reachable and controllable subspaces. We'll talk about the two gradients. Then we'll talk about tests for controllability. Right, so let's move on to the first topic, reachable and controllable subspaces. Just revise what these subspaces are and then move ahead. All right, so reachable subspace, and these are subsets of the state space. So let's say the state space is R. So Rn. So let the state space be. All right. So the reachable subspace is controllability from the origin. This is to the origin. So this is the objective of reachable subspaces is to find, guess, the controllable, find R. So from initial time to some time t1, which is a subset of Rn. So x1 belongs to the reachable subspace if there exists an input. So the input takes you from the initial condition to x1 in time t1. Similarly, to the origin means the set of states. So we'll denote this by script C. T0 to T1. So x1 belongs to C T0 to T1. If we have an input which takes you from x1 to x0 in time t using the input loop. So we are going to consider this as the initial condition. We have Gramians, so Controllability and reachability Gramians. So this is denoted by WR and this is WC. So I'm going to write down the definitions. WR T0 to T1. So this is phi T1 comma tau, B tau transpose, phi T1 comma tau transpose D tau, and the controllability Gramian is phi T0 comma tau, B transpose tau, phi T0 comma tau D tau transpose. So notice the differences. So these are the same. And then the only differences are we have to consider T1 and T0 in WR and WC respectively. So both of these are matrices. So WR and WC belong to Rn cross N. These are symmetric. So WR transpose equals WR and is positive definite. Similarly for WC. Alright. Now let's move on to the first question. Check the reachability and controllability of the following LTV systems. So the first one is x dot of t equals t square 0 u of t, and the second one is x dot of t equals 0 t 0 1 x of t plus t square comma 0. So the difference between the two parts is in this one we have the matrix A of t to be 0, and then we introduce a matrix AT here. B remains the same in both cases. Alright. So recall that the matrices C and D in the state space system do not play any role in determining the controllability or reachability of the system. So we won't specify it in any of these questions. So CT comma D of T play no role in determining the reachability or the controllability. Alright. So we have just seen what the reachability grammar is. Okay, so let me just write that down once more. WR T0 to T1 equals T0 to T1, and this is V tau V or transpose. All right. Since this is the reachability grammar, we will have T1 here. Okay. So we have that AT is a zero matrix, which imply that the state transition matrix is identical. So while T comma, let's say tau is identical. And we also have the vector B here, so let's substitute now. WR T0 to T1 as T0 to T1 identity times T square 0, T square 0 d tau, which is so we just have to integrate each element of this matrix. So we have zeros everywhere else except we have T1 to the power 5 minus T0 to the power 5 over 5. So now we have to determine whether the system is reachable or not. So this is a symmetric matrix and it's positive definite. So the system is reachable if determinant of, let's recall, LTV system, or it says the system is reachable and of WR is not zero. So in this case, it is 0, which implies that the system is not reachable. Alright. Now let's look at the second part of this question in which we introduce a matrix. See, A of t is 0, t 0, 1. B is as before. To compute the reachability grammar, we need to compute the state transition matrix. So to compute the state transition matrix for this LTV system, let's write down the equation first. x1 dot x2 dot equals 0 t 0 1 x1 x2 plus t square 0 u of t, let's just say u. So this has a nice form. We also saw in the previous tutorial session how to compute the solution for this kind of a system. So x2 dot is simply x2, which implies x2 is e to the power t x2 at 0. x1 dot is t times x1 plus t square. This implies x1 at any time t is simply like this now. Sorry, this is x2. So this is t e to the power t x2 at 0 plus t square u. So this is a system with only inputs, right? So we are computing. So this implies that we are computing zero state response. Because there is only input, right? Alright, so let's see. Just a second. So we have to compute the state transition matrix. So for that, I think we can do is just consider this without input. Just check once. It's going to be x1 gets here at time 0 plus some time 0 to t tau e to the power tau x2 0 t tau. So you can integrate this and I'll just write down the answer directly. This becomes x1 at 0 plus x2 at 0 is t e to the power t minus e to the power t plus 1. This implies that we have x1 of t, x2 of t as a function of the initial condition. This is 1 t to the power t plus this. Then we have 0 t to the power t. Simply e to the power t. So this implies that this is a state transition matrix y t comma 0. To write this down correctly, this is phi 0 comma t. Alright. So the reachability gradient from 0 to some time t is 0 to t. Then we have phi t comma tau, v tau, v transpose tau, phi transpose, t comma tau, d tau. So now we have to compute what is phi t comma tau. So this is going to be phi t comma 0, phi 0 comma tau. So we already have this. Phi 0 comma tau is simply 1 tau e to the power tau plus 1 0 e to the power tau. And this is the inverse. So inverse of phi 0 comma t. So you can compute the inverse of this 2 by 2 matrix right there, and then multiply with phi 0 comma tau to get phi t comma tau. I'm going to write down the final expression. So this is 1, 0 minus tau plus 1 e to the power minus tau plus e to the power t plus tau plus e to the power t. Then we have e to the power t plus tau. Okay, so now we'll substitute phi t comma tau in the expression for the reachability gradient. And we also have the b vector, so we get phi 0 to t. It's actually 0 to t, t to the power 4, 0, 0. Again, as in the previous part. And this is simply t to the power 5 by 5, 0 and 7. We saw before that the determinant of this is 0, which implies that the system is not reachable. So I hope that this question was clear. Now let's move on to the next one. Now we have questions to check the controllability of the following LTI system. So we have x dot equals -7, -2, 6. We have 2, -3, -2. We have -2, -2, 1. X plus, this is 1, 1, 1 minus 1, 1, 0. So this is a two-dimensional input then, R2, and X is in R3. We have n equals 3, and the controllability matrix C is given by B, AB, AB square, sorry, A square B, R n minus 1 B. So for our case, we simply have B, AB, and A square B. Okay. We simply have to compute these two quantities and substitute them in the controllability matrix. So AB is so let's compute -7 -2 plus 6, then -7 plus 2, then 2 -3 -2, 2 plus 3, -2 -2 plus 1, -2 plus 2. So this becomes -3 -5. And then we simply have -3, 5. And then we have again -3 and 0. We have to compute A square B. This is simply A times AB. So let's write down A first. -7 -2 6, 2 -3 -2, -2 -2 1. Then this was so you can compute this and I'll just write down the answer directly. So we have 9, 25, 0, 0, 0 and -25. It's from the controllability matrix. So C is B first. So 1, 1, -1, 1, 0. Then we have AB. So -3, -5, -3, 5, -3, 0. And then finally, the last two columns. So recall that the entire system is controllable and only if the rank of the controllability matrix is n. Okay. So if it was the controllability matrix was a square matrix, we could easily compute the determinant and then determine its rank. But let's see here, this is not a square matrix, so we'll have to find out if the 3 rows or any of the 3 columns are linearly independent or not. So let's mark them. This is row 1, row 2, and row 3. So to find out if these are linearly independent, we just have to compute these coefficients. So alpha 1 R1 plus alpha 2 R2 plus alpha 3 R3 equals 0 should imply that these 3 coefficients are 0 as well. Then the rank would be 3, right, for rank. So right now we have n equals 3. Okay, so let's see. So this is 3 by 6 and the rank is going to be less than or equal to a minimum of 3,6. So the rank is going to be either 3 or less than 3. Alright, so now let's see the linear combination. So we would have alpha 1, 1, 1 minus 3, 925 plus alright, so we'll have a lot of equations. Let's see. First one is going to be alpha 1 plus alpha 2 plus alpha 3 is going to be 0. Let's see where alpha 2 is going to be 0 here. So alpha 1, so alpha 3 is 0. Alright, so this implies that alpha 1 is 0. So I'm going to write this down. 3. Then we have, this implies that alpha 2 plus alpha 3 is 0 or alpha 2 is equal to minus alpha 3. Now let's compute the let's So what we can do is compute for this, this, and this. So we have alpha 1 minus alpha 2 plus 0 alpha 3 equals 0, which implies alpha 1 minus alpha 2 is 0, which implies alpha 1 equals alpha 2, which is 0. And these two imply that alpha 3 is 0 as well. So we have that the rank of the controllability matrix is indeed 3, which implies that the LTI system is controlling. So next we have a similar question on which we have to comment on the stability, on the controllability of the LTI system. So let's see. Consider the following system. X dot is 1 0 0, then 0 0 minus 1, x plus some constants which are unknown, b1, b2, b3, u. b2, b3 are unknown scalars. So there are two parts to this question. So in the first one, we have to provide an example. Use for b1, b2, b3, for which the system is not controllable. For the second part, we have to provide the values for which the system is controllable. So provide an example. So let's start with the first one. This is a third order system. So the controllability matrix is going to be BAB A square B. So let's compute this quickly. AB is going to be 0, B1, B2, B3. So simply B1, 0, and minus B3. Alright, then we have B square B, which is A times AB, 1, 0, 0, 0, 0, and minus 1, times B1, 0, minus B3. So this is simply going to be 1, 0, and B3. Let's form the controllability matrix. B1, 0, minus B3, B1, 0, B3. Alright. So let's see. So its rank of the controllability matrix has to be 3. All the 3 rows should be linearly independent. So must be linearly independent. So this is the first row, second row, and third row. So this implies that a whole row cannot be 0, right? So R1 cannot be 0, R2. It says if the system has to be controllable, we want values of V1, V2, V3 for which the system is not controllable. So for the system, not controllable, can choose. So let's see, the simplest case would be V1 is 0, V2 is 0, and V3 is 0. So this would make the whole second row 0. This would make R3 0, and similarly R1 0. Because this would imply that the determinant or. And now we can quickly move to the next part. We already have the controllability matrix. So we want the rank not to be 0. So, rank to be exactly 3. So for the system to be controllable, C should be exactly equal to 3. So no row should be equal to 0. So let's say that B2 cannot be 0. Okay. So let's say that B2 was 1. And similarly, if we choose B1 to be 1 and to be 1, then the controllability matrix would be we just have to check if this is full rank. So this is a square matrix, so we just have to compute the determinant. Alright, so determinant is spanned along R2. So 1 time 1, 1, minus 1 and 1. 1. So therefore this choice of B1, B2 And Week 3 is the system which is controllable. So this is just one example. You can also choose other values of V1, V2, and V3. And check if the system is controllable or not. Or let's move on to the next question. All right. So now we have question 4. So consider the harmonic oscillator. The control signal U satisfying the following state space equation. Second order system. This is 0, 1, and this one 0. All right. So now we have 3 parts to this question. The first one is to compute the controllability gramming. Zero to 2 pi. 2 pi is the final time, right? Then we have to find an input. So does there exist a control U which transfers this state 1, 0 at time t equals 0 to 0, 0. This is because we are talking about the controllability here. So we are talking about reaching the 0 state from a non-zero initial state at time t equals 2 pi. Third part, so suppose Q is a piecewise constant function of time. Of the following form. So I have u of t equals some constant u1 for the time period 0 to 2 pi by 3. Then we have some constant u2 for time 2 pi by 3 to 4 pi by 3. And then finally u3. So the question is, we have constants one u2 u3 such that transfer the state 0, 0 to again the origin at t equals to pi using the above view. So we already have a system and we have to find out the controllability planning. And this is an LTI system. So first we will find out what the state transition matrix is. So we have A equals 0, 1, minus 1, 0. So always remember that this is the state matrix for the harmonic oscillator. This would lead to a very simple state transition matrix. And then we also have B as 0, 1. Alright, this is an LTI system. So the state transition matrix, let's say phi 0 comma t is simply e to the power at, which is nothing but the Laplace inverse of Si minus A inverse. Alright, so now let's compute these. Si minus A as S minus 1 and 1. So Si minus A inverse is going to be, this is a 2 by 2 matrix, so 1 upon determinant of the matrix. This is S square plus 1. Then we swap the main diagonal entries, and then these are going to be of opposite sides. This is simply S upon S square plus 1. So using the partial fraction expansion, you can compute Laplace inverse of Si minus A inverse. So using the Laplace inverse of S upon S square plus 1. So we don't need the partial fraction expansion in this case. We have the direct formulas for 1 upon S square plus 1 and S upon S square plus 1. So I'll write those down directly. So e to the power at is simply cos of t. So omega is 1 here. You can just check the Laplace inverse of, I guess that's omega upon S square plus omega square. Something like that, I guess. We'll just check once. So this is going to be sine of t. again minus sign, and then cos. Alright. So now we have the formula for the controllability grammar. So we have WC from 0 to 2 pi. Tau V transpose. Then we have phi tau transpose. So since we are talking about controllability, so this is going to be the initial time 0. And this is an LTI system. So this is simply phi 0 comma t. Just 1 second, I'll check. Okay, sorry. This is phi t comma 0. So phi 0 comma t is just going to be the inverse of this matrix. Alright, so we have B already. This one, we just have cos of P and then minus of. Have phi B transpose and phi transpose. So let's compute this quickly. Cos t minus sin t cos t, and then B is 0 1 0 1 and then transpose. So cos t so this is simply, and then we have minus sin t cos t. So this is sin square t minus sin t cos t, then minus sin t cos t again, and cos square t. Okay, so the controllability Gramian is going to be the integral of each of the element of this matrix. So we have 0 to 2 pi sin square t sin t cos t, and then we have 0 to 2 pi cos square t dt. Alright, so you can compute this quickly and I'll just write down the final answer. This is pi 0, 0. So that was part A to complete the controllability grammar. And now in the second part, let's scroll up for a second. So we have to find out if there exists a control U which transfers the system from 1 0 to 0 0 in time 0 to 2 pi. Alright. So we have already computed the controllability gradient, and the determinant is non-zero. Also, we have the controllability matrix, which for this case is simply BAB because it's a second order. So I'll just write this down directly, 0, 1, 1, 0, which implies that this is full rank. This is the identity matrix, which implies that the system is controllable. So therefore, we can construct an input which takes the system from 1, 0 to 0, 0 in the time interval 0 to 2 pi. Alright. So recall that. So if you have some state x1, which is let's say phi 0, 2 pi, one second, so let's recall the theorem first and then we'll continue. So this is theorem on slide 20. Second. So we already know that the controllable subspaces of WC T0 to T1. So we already know that the system is controllable. So for us, the controllable subspace is the whole of Rn, right? So if I'm going to write down the statement, so moreover, if the state x0 is in the image of the controllability grammar, then the control ut equals minus b transpose phi t0 comma t eta naught can be used to transfer the state at v0, which is x naught, to x at t1, which is the 0, 0. Alright. So you already have the initial state. So according to the question, 0 is, let's see, 0.10 I guess. If 0 is 10 transpose, and we already have the controllability gradient, so eta naught is WC inverse. So now you'll appreciate why we need the controllability gradient to be invertible. So eta naught is simply, this was a diagonal matrix, so this is simply going to be 1 by pi, 0, 0, times 1, 0. Alright, so this is eta naught, and T of t is simply minus B transpose. So phi 0, comma 2 pi. So let's write down the time. So u at any time t is going to be at time t, phi 0 to t, eta naught. So v is 0, 1. But we also had phi 0, comma t. Let's see. This is simply cos minus sine, sine cos, and we have eta naught. So this means we have sine t cos t 1 by pi and c, which is simply minus 1 by pi sine t. See, so I think there is another missing. Just a second. All right, so if we have some where x0 is c0 comma 2 pi, so this is not correct, times some eta is x0 minus phi 0 comma 2 pi x1. So this is actually 1, 0 there, and this is 0, 0. So this whole quantity is in the range of WC. Pi. So eta is simply WC inverse 0 to 2 pi times 1, 0. So phi 0 comma 2 pi is simply this. Yes. So this is phi 0 comma t. So at t equals 2 pi, this is simply the identity matrix. So we have 1, 0, 0, 1, and then 0, 0. So WC inverse is, as we just saw, 1 by pi, 1 by pi, 0, 0. This is 1, 0. Alright, yeah, so I think this is correct then. UT is simply minus 1 by pi sine of it. So we can also verify this by using the variation of constants formula. So x1, which is 0, 0 transpose, is going to be e to the power at x0 plus 0 to 2 pi power at t minus tau e tau u tau t tau. So e to the power at in our case is simply, let's scroll back up. Minus sine times 1, 0 plus 0 to 2 pi cos of t minus tau sine t minus tau. Let's write this down. D was simply 1, 0, and we're considering u as minus 1 by pi sine of t. So tau here. D. So it's simply cos t minus sine t. So at t equals to pi, we have comma 0 again plus this is going to be 2 pi actually. So t is 2 pi. Tau everywhere. We simply have cos 2 pi minus tau minus sine 2 pi minus tau times 1 by pi sine tau. So we have 1, 0. So cos 2 pi minus tau is simply sine tau. And then minus sine will be, let's see. So we have plus sine tau again. So this is cos of tau. 0 to 2 pi minus 1 by pi sine tau. So this becomes, I'm going to take this outside. I have 0 to 2 pi cos tau sine tau. And then we have 0 to 2 pi sine square tau. So let's see. So I have sine square tau is going to be just pi. And cos tau sine tau is going to be c. So I think this is so I think there was a sign problem here. I think we can check. I guess this is here and plus here maybe. Anyways, you can check the calculations and see if this is comes out to be equal to 0, 0 at the end or not. Alright, and then we finally have the third part. This is alright. So this will also be clear in this next part. So the solution of the ATS system is, sorry, So t as phi t comma 0, x0 plus 0 to t, t comma tau, b u tau d tau. And that piecewise continuous input is also given to us. So t is between 0 to 2 pi by 3, then pi by 3, and finally from 4 pi by 3 to 2 pi. Okay, so t is 2 pi here. So x of 2 pi is phi 2 pi comma 0, x0 plus 0 to 2 pi, phi 2 pi comma tau, v u tau d tau. So we have already computed what phi 2 pi comma 0 is. Sorry, phi 2 pi comma tau is, and you can just multiply this by v. So I'm going to write this expression directly. This is sine 2 pi minus tau, cos 2 pi minus tau, and this is minus sine tau cos tau. Yeah, I think that was the problem when you were verifying the answer. Alright. So it's just as 1. Integral in 1 can be computed. So notice that we have a piecewise continuous input, constant input. So the integral from 0 to 2 pi can be broken down in 3 intervals. So that's what we're going to do now. So the first one is for time 0 to 2 pi by 3. Ut is equal to u1. So we have the integral 0 to 2 pi, then minus sine tau cos tau. That's always going to be the same, this quantity. Then it's simply u1 times theta. So what we have to compute is actually the integral of this. So this is, sorry about this. This is from the interval 0 to 2 pi by 3. So this is going to be cos tau from 0 to 2 pi by 3. And then sine tau from 0 to 2 pi by 3. So this is simply u1 times minus 3 by 2 under root 3 by 2. Okay, similarly, we have two more intervals, so I will write that down quickly. So for t between 2 pi by 3 and 4 pi by 3, we have the integral sine tau cos tau. Then we have u2 d tau. So you can compute this, and the answer is u2 times 0 minus root 3. Similarly, for the last time interval, we have for 4 pi by 3 pi. The interval is minus sine tau cos tau u3 d tau So you can compute this, and the answer is 3 by 2 minus u3 by 2 times u3. Alright, so what we can do is sum these up. So this is, let's say, 2, 3, and 4. You can sum these up and substitute this in 1. So x at 2 pi, which is 0, 0, is 1, 0 plus minus 3 by 2 u1 plus 3 by 2 u3. 3 by 2 u1 minus under root 3 u2 minus under root 3 by 2 u3. So the objective is to find out if there exists constant u1, u2, and u3. So we just have to solve this equation. Okay. So let's see what the equations are. We have minus 3 by 2 u1 plus 3 by 2 u3 plus 1 equals 0. This implies that u1 is u by 3 plus c. Similarly, we have the next equation. So under root 3 by 2 u1 minus under root 3 u2 u3 equals 0. So we have these two sets of equation, and we're going to assume, let's say that we assume that u3 is some constant c, because we want to solve for 3 unknowns. Two equations. So we're going to assume that this is some constant. So this implies that u1 is 2 by 3 plus c and u2 is 1 by 3. Just check if this is correct. Half of u1 minus u3. Yeah. Okay. So therefore, the vector is, or let's say, therefore there exists constant which transfers the state from 0 to 0, 0 in the time interval equal to 2 pi. Alright, so this was a question which showed how to actually find the input, given that we have proved that the system is controllable and we have also the controllability grammar hypothesis. Alright, so let's move on to the last question. So you have to find out whether the discrete time system is reachable and controllable or not. So consider discrete time ATI system. x at k plus 1 equals 0, 1, 1, 1 x of k plus 0, 1 of k. So comment on the reachability of the system. All right. So let's first, this is a time invariant system, a discrete time invariant system. So the controllability matrix is still B and AB. So this is 0, 1, 1, 1, and this is 1, 0, which implies that the system is controllable. So we are just going to talk about the controllability of the system. If the discrete time discrete time invariant system is controllable, then this means that any state S1 can be reached zero state so in a finite number of steps, because we're talking about discrete time. So by applying inputs. So this is given by u of 0, u of 1 till u n minus 1. So right now n is equals to 2. We have u0 and u1. So let's assume that we have some state x1. So let's assume that x1 is actually AB. So therefore this means that AB is actually 0, 1, 1, 1 times 0, 0. Just 1 second. plus some 01, let's say UK. AB equals 0111. Okay, so let's say that we have at most two steps. So k equals 1 and start from k equals 0 and 1. So I'm going to write this down as thus the control. So I have u0 as a and u1 as b minus a. We'll transfer the state from origin at k equals 0 to ab at k equals 2. So let's say that k equals 0, I had x at 1 is simply u at 1. And then x at 2 is actually a times u at 1. 0, this is at k equals 1. Okay, let's just compute this again. So we have x at k plus 1 equals a x at k plus b u of k. So at k equals 0, initial time, I have the first state as x0 plus b u0. So x at 1 is simply b times u of c. We have at k equals 1 x at 2 becomes a at x1 plus b at u1. So u0 and u1 are scalars. This implies we have a b u0 plus b u1. So now let's see. 1 1 times summary 0 plus 0 1 u1. It's going to be simply 1. So if we want a b to be x2, so in terms of, let's say u1, u0, we have 0 and 1, and then 1 1. So this is what we had here. Alright, so this star equation implies that there is u1 and u0 computed like this by taking the inverse of this matrix. That this control will transfer the state from the origin to AB in 2 time steps. Alright. So therefore, we have already seen that the system is controllable by the controllability matrix, and we have also found the input, the sequence of inputs, which will transfer the state from 0 0 to any arbitrary state AB. Alright. This was about the controllability of the discrete time, linear time invariant system. Alright, so let's end for today. Thank you.